Assalamualaikum and hi everyone, this is Dr. Shazira. In this video, you are going to see how to prove a symmetric positive definite matrix, which is the criteria for Cholesky method. There are two ways to prove an SPD matrix. The first one is by using definition, and the second one is by using the theorem. Alright, so by definition, a symmetric matrix A is positive definite if we can prove that the vector x times the coefficient matrix A times the vector x must be always positive for any x which is not equal to 0. Okay, 0 elements. For example, consider this matrix A here, and by definition, the X transpose, okay, this is X transpose, multiply with the coefficient matrix A times the vector X, okay, can be written in this form. All right, and then if we multiply these two, then we have this long expression here, which can be simplified into this. Okay, but up to this point, it is still not quite clear that the expression will always be positive because of this guy here, these two terms here, it could be negative. So the process here is to think or to try to manipulate the expression, to rewrite the expression to see whether, we can come out with a positive expression. So normally for the positive expression, we can ensure we will have a positive expression if the terms in the expression involve the square, term with the square, and we have the addition. Okay, the same thing that you can see at the first three terms here, you can guarantee that they are always positive. Okay, because no matter the value of x1, x2, x3, you always square that term. So they will be always positive. But these two, okay, can be negative. So now we need to manipulate. Okay, try to manipulate to see whether we can get the positive term. So for this example, okay, if we write, so the idea is to, reproducing, okay, rewrite in a different form, okay, which is equivalent to the previous expression. So we want to have x square and x1 square and x2 square, and then we want to relate with this one here. Okay, so we'll have x1 plus x2 square. So up to this point, we have x1 square plus 2x1 x2 plus x2 square. Okay, but in the previous expression, we have 3x1 square. So meaning that we need to add with 2x1 square. Okay, and in the previous, we already have the 3x2 square. So it should be plus 2x2 square here. Okay, so by that, we have covered this guy, that guy, and that guy. Okay, but we still have 3x cubed square. Okay, 3x3 square minus 2x2x3. Now we need to think of, how can we rewrite the terms in the form of x2 and x3. Okay, so since we have the subtraction, okay, so maybe we can have in the form of plus. Okay, we always want to have the plus to ensure it is always positive. Okay, so now let's put x1, x2 minus x3 square. Up to here, we have, x2 square minus 2x2 2x3 plus x3 square. Alright. Okay, so it means that we need to have minus x2 square, right? And then we need to have plus 2x3 square. Okay, so now we can simplify the expression. So now we have x1 plus x2 square. Okay, and then we have plus x2 minus x3 square. And then you can see we have 2x1 square. Okay, and then you can see this and this can be simplified. As x2 square plus at the end we have 2x3 square. So now you can see this expression here is always positive. Regardless the value of x1, x2, and x3, okay, you now have x transpose times A times x is always positive. So this is always positive. Okay, so therefore we can say that the matrix A is an SPD matrix, symmetric, positive, definite matrix. Okay, that's how you prove by using definition. But the difficulties to some of the students is actually on the manipulation part. Okay, so from here, sometimes it is not that easy to come out with, the expression at the last line here. Okay, you need to do a lot of exercises, okay, on this, and then the manipulation, the algebraic manipulation should be naturally comes to you. But anyway, okay, we have another way to prove an SPD matrix, which is by using definition. By the theorem, you need to show that you satisfies all of these four conditions, okay, in order for you to say that A is an SPD matrix. Okay, but before you proceed with number 1, 2 and 3 and 4 here, first of all you need to make sure your matrix A is a symmetric matrix. Okay, otherwise this is not a symmetric, yeah, positive definite. So I'm taking the same example as before. This is your matrix A. So clearly, okay, this is symmetry. Okay, so if we look, if you slash out the main diagonal, and then you can see the elements at the upper part, okay, is the same as the elements in the lower part. Okay, in opposite direction, they are um, the same. Okay, so A is a symmetric matrix. Okay, and then we can proceed with the theorem. Okay, so number 1, you need to show that A is a non-singular matrix by calculating the determinant. Okay, determinant of A must be not equal to 0. So you can use your calculator to get the determinant. So for this matrix A here, the determinant of A is 21. Okay, so clearly this is not equal to 0, so you satisfies the first condition. So the second one, the diagonal elements are positive. Okay, so A11 is 3, okay, A22 is also 3, E33 is also 3. So all of them are positive, so we are okay with that. So A11 is 3, so positive. A22 is also 3, positive. A33 equals 3, so positive. All right, so okay with condition number 2. Condition number 3, the max of absolute AKG must be less or equal to the maximum of the absolute of AII. So what it means by that, so the AII here is actually the elements of the diagonal in terms of absolute value, and the left part here other than the diagonal. elements other than diagonal. Okay, so it means that, on the left part here, you take out the maximum value, the element with the maximum value in terms of absolute value, okay, um, from the elements other than the diagonal. Okay, so you take the maximum one and see whether you satisfy this. Okay, is it less or equal to the maximum um, from the diagonal element? Okay, so for this case, so you see, if we take the right side first, so we have the diagonal elements 3, 3, 3. So in terms of absolute value, they are all positive 3. So the maximum would be 3. So you take the right side is 3, and then we want to see whether we are satisfying the maximum um, of the rest of the elements other than the diagonal. So you can see other than the diagonal, okay, so we have elements at the upper part here, okay, as well as the elements at the lower part. So the maximum out of the upper and the lower part is positive 1. Okay, so it is clearly that 1 is less than 3. So we are okay with that. Okay, so we satisfy condition number 3. Condition number 4, aij square must be less than aii times ajj. So this one, you are actually checking for each element other than diagonal, because you can see here I cannot be j other than diagonal. Okay, meaning that we want to show that A12. So we start with the element A12. We didn't do for A11 because I equals J at that point. So A12 square, okay, which is somehow, since A is a symmetric matrix, so it is equivalent to checking for A21 square. So we want to check whether A21 square, okay, is it less than A11, A2, A11, yeah, A11 times A22. Okay, so this is A12 is 1, okay, square, and then okay, is less than A11 is 3, and A22 is also 3. So we satisfy on that. And then we check for A13, which is the same as checking for A31 square. So we are questioning that. A33, A11, or A11 times A33, doesn't matter, okay? They will be the same. So A13 is 0 square, and then at the right side we have 3, and then another 3. So it is clearly, okay, 0 is less than that. Okay, so we are okay with that. And last one, we are checking for A23 square, which is equivalent to checking for A32 square. Is it less than A22, A33? Okay, so A23 is negative 1, okay, square. Is it less than, again, 3 times 3? So we are okay with that. Okay, so we can see this matrix A here, okay, before anything, it is symmetry. So we are okay with the symmetric condition. And then, you see that we are satisfying these 4 conditions here. So we can say that A is an SPD matrix. All right, so write down. Since all conditions satisfied. Therefore, A is an SPD matrix. Alright, so those are two ways of proving an SPD matrix. First, by using definition. Second, by using the theorem. So read your question carefully. Okay, determine or identify whether the question asks you to prove by definition or by the theorem. Okay, if the question didn't say anything about which way, then you can choose. Okay, which way that you prefer to use. All right, so I hope that one is clear. Okay, so see you. Bye bye.